Good morning, everyone. My name is Rich Lovedahl. I'm one of the senior engineers here at Allen Block, and I'd like to thank you for taking some time out of your day to sit with us for this one's an overview of the program, so it'll be about 30 minutes longer if there's questions, and but I do thank you for being part of today's session. And really what we're focusing on today is the new release of AB Walls, and it is going to be coming out very soon. It's not quite ready. We are working diligently every day. We do all our programming in-house, and we're in the checking process, making sure as best we can to get everything taken care of. So when it releases to you, it's in tip-top shape. But the AB Walls plus Terraces using limit equilibrium for the internal design is really the focus of today. And after today's session, I'll definitely send out an email to follow up with everybody. And the update for AB Walls will be like any other one. If you currently have AB Walls on your PC, you'll double click on the icon, and if there's an update available, it will just please say yes to that update, and in 30 seconds or so, you'll be up to date. So it'll be a standard update. And those of you that do not have the software, please feel free to respond to the email that I'll send out tomorrow, recapping today's events, and request a copy, and we'll get you that at ASAP. All right. Well, with that, let's get started and start talking about terraces. So here is a simple section that you're going to be able to see and design in AB Walls plus Terraces. It's obviously three terraces. It's got some minor setbacks. And what you'll find, and I'll cover it in later slides, but you as the designer will be able to go into the software and design virtually any height, any number of terraces, and any variation of setbacks to best fit your site design. And it's all at your fingertips, and it's going to be very easy to use. So, but for those of you that have been using AB Walls, I want to put you at ease that the standard AB Walls design methodology and the 3D modeling functions have not changed. You could go in and do the wall just like you normally have and not see anything changed for the terraces, because we've integrated the terraces into the standard wall application, and we think that we've made it very easy to transition to using the more complex structures like terraces. So, all right, so let's talk about terraces. So, as wall designers, we know what we're looking for. Wall designs of any shape or size, we need to start with external stability. Make sure our sliding and overturning and so forth are adequate. We're going to be looking at them for each individual wall within a terrace. Each terrace or each wall cross section, you'll have the flexibility of do different heights or wall offsets. You'll be able to do surcharges on top of any terrace or, of course, above the top wall. You're going to be able to analyze slopes above any of the walls as well as the top wall. And the ability to do varied soils for any one of the terraces. So I'll have a slide where I'll show you how we've color coded if we decide to have different friction angle soil in each one of the terraces. Now, I'm not sure how much it's going to be used by an individual, but we certainly wanted to give you the freedom and flexibility to do as close to as-built conditions as possible. So the seismic design capabilities are built into the Bishop's model, and then, of course, the internal design analysis. And what we're here today to talk mostly about is limit equilibrium. And I should say, as I get started, if you do have questions, feel free to type them in the sidebar. The way the webinar is set up, I do have everyone muted. It's kind of part of the system. I will have some time at the end of the presentation. I'll go through those questions, or feel free to reply to that email I'm going to send out tomorrow, and I'm more than happy to reply to that or take personal calls. So we're here to help. All right, so let's take briefly about the external design calculations. So really up until now, external stability calculations are something you'd really have to do by hand, maybe set up an Excel spreadsheet or something, but now it's built in automatically done based on the geometry that you input for the cross section. And I'll talk about the red envelopes and the yellow slip arcs here in a few minutes. But for every terrace, we're looking at the sliding, overturning, and bearing safety factors and how they relate to each other as surcharges or so forth. So pretty standard external stability calcs will continue into the terrace section. Here's a couple slides to show about the user-defined offset. So when I was putting this together for the presentation, I was envisioning a set of terraces to fix a hillside that might be overlooking a wetland area, and maybe we've got an 11-foot offset where there's going to be a bike path put in or a walking path. And so now with AB walls plus terraces, you're going to have that ability to do the geometry that's required for your site, as well as put surcharges appropriately on the walls. All right, so slopes above, just like the AB walls standard, we can do AB slopes above any terrace, any top of the wall. And then I've got the color-coded showing here that every terrace has the ability to have different unit weights as well as friction angles input for the wall, for each one of the walls. All right, so let's jump into limit equilibrium. So what's making this possible is just that. It gives us a much more detailed analysis of the mass because it's using a global stability modeling process. So LEM was developed by Professor Dov Lazinski after many years of research. Those of you that know Dov, he is kind of a godfather of the segmental retaining wall and global stability melding of the two methodologies. He's a great resource. He is retired from the University of Delaware, but I think today he's working as much as he ever did because he enjoys what he does so much. He just keeps going. So limit equilibrium has been adopted by Federal Highway Administration, by AASHTO, and by the NCMA as viable alternative designs for internal stability calculations. So it's a very detailed analysis of the mass, and it uses a modified Bishop's global stability modeling program to determine the amounts and locations of loads anywhere along any grid layer within the wall. So those of you that know even a little bit about global stability, you know that how it works is that above any slip arc that's analyzed, you're going to develop forward sliding forces along that slip plane. And if that slip plane does not have enough internal friction along the slip plane, you're going to have positive forward forces. And those positive forward forces have to be dealt with or captured by the grid layers to make it stable. So the program develops thousands of slip arcs along each cross section, and wherever the cross section grid intersects a grid layer, the LEM tells the designer the exact load required by that geogrid to make it stable. And we're going to call each one of those intersected values, or the values at those intersection locations, the T required at that given spot. And if we look at all of the slip arcs that cross a particular grid layer, we're going to develop what's shown in red, the T required envelope. Those T requireds are what we're going to have to deal with when we get to the design part. So I'm going to stop just for a second and just remind everybody, just like years past, if you're familiar with the internal compound stability that Alan Block and the National Concrete Masonry Association introduced back in 2007, it's very important to understand that the Bishop's model for limit equilibrium and the ICS calculations, they do not replace the need for a full global stability analysis. Because every one of the slip arcs that are developed by the Bishop's model for limit equilibrium never go below the wall. The entrance points start directly behind the cap unit and go well up the slope behind the wall. But all of the exit nodes come out the face of the wall. We're going to use the joints between the courses as our exit nodes. Global stability does not have any limitations, so you're going to have exit nodes that are well below the wall, meaning they're looking at the entire global stability of the entire site. We're using the global stability model of bishops to determine the forward sliding forces within the mass. Okay, so not a replacement for global stability. So limit equilibrium works with the idea of um, equilibrium within the mass when you have a global stability safety factor of 1.0. So it may be too simplistic of an idea, but we're just looking for that, what Dove calls, or Professor Lazinski calls, the baseline solution. What is the bare minimum that's required from the geogrid to create equilibrium? Now, some of the slip arcs, if they're very flat, just like a global stability model, you might not have any forward sliding forces because the friction along that slip arc is enough to resist the forward sliding forces. But those ones that start more closer to the back of the wall are much more vertical. So we're going to have much more of a slide. Imagine a playground slide that's much more vertical than one that's very flat. You're going to get much more forward push, and that's what's being transferred to the geogrids. So in the baseline solution, we're just looking for that maximum load that's developed along each one of the grid layers. And the T required values along that length of grid develops that envelope that I showed you in the past slide. So let's take a look at a real basic line drawing to talk about what that envelope looks like. So the T required envelope develops really three different things for the designer to look at. What is the maximum T required along that line, and where is it located? So I'm represented it roughly in the center. It's not necessarily always in the center, especially in terraced applications. It kind of floats around where it happens. And then the pullout requirements for the front end and for the end of the grid are shown here as simple arcs. And I'll talk about the T required that exceeds those arcs here in a slide or two. So once again, for each slip arc, those forward forces from the Bishop's model are divided equally among any of the grids that slip arc crosses. So it may seem simple, but if we have X number of, or X magnitude of a forward force, we simply divide it by the number of grids, and that grid then has to be strong enough to carry that load. So if we look at the bottom slip arc here, we are crossing 6 geogrid layers. And so those forward sliding forces determined for this one slip arc are divided into the 6 layers of grid. And those are the T required. And in this case, the diamonds that we're showing in the program, those are the worst case or the T max, and thus those T max locations. So what we're going to do in AB walls is we're going to give you the worst case slip arcs that determine those T max, and we're going to put a spot on the curve to show you the T maxes. So we're showing in this particular image 1, 2, 3, 4, 5, 6, 7 different slip arcs. So it took 7 different slip arcs to yield the T max for all the grid layers from bottom to top for this particular structure. Every structure will be different. That is the beauty of bringing a global stability design into the wall design. It is taking slip arcs throughout the entire wall and breaking it down into analyzing one slip arc at a time and getting a T max and a T required at every grid location for every slip arc and every intersection point. So lots of data being harvested here. Okay, so the P front and the P end pull-out capacity curves, they're developed by that standard GeoGrid pull-out equation that we've all been using for years and years. You have the embedment length, you have the height of the soil above that that portion of grid that's embedded, the unit weight of soil, the friction angle of the fee, and grid interaction. This is the common equation that we've all used. If you've been doing any kind of wall designs, this is a standard pull-out equation. We're going to use that at the front end of the grid and ignore the block just for part of the time, and I'll tell you why in a minute. And at the tail end, at the end of the grid, we're going to use it as we typically would. And you can see how it starts from 0 because there's 0 embedment, and then it increases fairly rapidly as the embedment increases. So if the Bishop's model yields T required values that exceed the end of grid pullout capacity, it does not mean that the grid is not embedded far enough or there's somehow a pullout failure. What it means is that those excess forces must be transferred or shared to other grids that are crossed by that particular slip arc. So therefore the P end capacity is the maximum capacity that we can use to resist those forward sliding forces for this particular grid, for those particular locations. When we reduce the load at the tail, at the end of the grid, those excess forces then are redistributed to the other grid layers. Okay, so let's take a look at this same example again. So if on grid layer 6 we needed to reduce the capacity there because of pullout limitation, we would then equally divide that extra amount, that excess amount, into those 5 remaining layers of grid. So for simple math, if I'm looking at, say, maybe I have 700 pounds of T required at the end of the grid, but I only have pullout capacity of, say, 200 pounds. Well, that leaves me 500 pounds of excess, and obviously I chose that for the easy math for today's conversation. So each one of the T requireds for the other 5 layers will increase by 100 pounds, so that all of those loads are put into that baseline solution, and now the new T required at these locations will reflect that additional 100 pounds. So it's pretty straightforward, I think. I'm hoping that that idea is being passed along. That's how we're handling the end of the grid. So at the front, it's sort of similar in that we're looking at that same pull-out soil capacity curve starting at the back of the block. So for the moment, we're ignoring the block because ultimately what we're looking for is what's required by the connection. So if there are any T required values that exceed the front end pullout capacity, their excess forces then are really what's considered the connection capacity. And Dove terms that T naught. So T naught is simply the translated value of the front curve to capture that excess T required value. So you can see in the lower picture, all we're doing is simply translating upward to make sure that a new curve is going to be completely encapsulating any of those excess T requireds. And that the magnitude of that transfer upward, that is simply the minimum connection capacity that's required to have equilibrium within the system. Okay, pretty straightforward, I think. I hope. So now that we have the baseline solution, we did all of this Bishop's model and all of this analysis on the Bishop side and the T requireds to get basically three things: T max, T naught, that's the connection, and then make sure that we're reducing the end as needed for the pullout requirement at the end. So what does AB Walls do now with these items? And some of you probably already have guessed that, well, we're going to use this for real world applications. And complex structures such as terraces have been around forever and ever. And basically, up until now, we had to make some design assumptions in any software package that does SRWs. But now, AB Walls plus Terraces have it built in right here at your fingertips, and we're making it easy for you. So what AB Walls does is we're going to start with the basics. If any of you have used it, and I think many of you have based on the list of attendees, you know that when you enter AB Walls, the first thing you do is you tell the program what block and what grid combination you want to use for your project. Then you move into the wall geometry. You input the elevation. You input the plan view. So now you're building effectively a 3D model. You got the height, you've got the length, and then when you get to the section part, you're building the depth. So in the cross sections, or I should say in the panels, you get to choose how long of a segment of wall that you want to analyze in one cross section. And AB Walls allows you to do any number of lengths of wall to design any number of different cross sections along the wall. And the seamless part of the integration with the new AB Walls Terraces, you're going to be able to have, say you have 5 panels that you want to analyze. So you have 5 cross sections to design, but maybe only 2 of those are terraces. You're going to be able to do 1, 2 as standard walls, 3, 4 as terraces, and the 5th one as a standard wall again, if that's the geometry of your wall. Again, we're providing the flexibility for you guys as the designers to build or design your walls as close to as-built conditions as possible. And then the last 2 are important because we're going to follow the same best practices that we've been preaching for ever and ever. 60% of the wall height should be used for your minimum grid lengths. And for terraces, it's simply 60% of the overall structure height. Now, that's going to be the starting point. You guys, as the designers, can make adjustments to lengths as you wish. And then, of course, we're going to use, or at least for our default, we're going to have the 2-course grid spacing, which is the industry's best practice methodology for any wall, whether it's a terrace or not. 2-course spacing builds a high-quality wall that'll last forever. So once we have the basics, now AB Walls can start to compare. So we're going to take the T max along every grid, and we're going to compare it to the long-term allowable design strength for the grid that was originally chosen by you when you entered the program. If by chance you've chosen a grid that's not strong enough to exceed the T max plus whatever safety factor you choose, the default for the program is going to be 1.5. You would have to go and grab a stronger grid and input it at that point. And then likewise for T naught. The T naught is the maximum connection requirement that's been determined from the Bishop's baseline solution. And you need to make sure that the block grid combination has a connection capacity that also exceeds that T required, or that T naught at the face of the wall. So that's the basics of what the baseline limit equilibrium does and how we're going to use it into the program. So the connection capacity, again, is automatically built in when you've selected the block and grid combination. And Allen Block, just like all our competitors, we have connection capacity testing done with all our block and grid combinations, And again, it's built right into the program. So kind of to sum things up a little bit, that LEM provides the designer an extraordinary level of information. Every inch or so on any grid of any wall, you're going to have a T required that's available, and you're going to be able to determine those T maxes. So it's a wealth of information within the wall design. That's what global stability brings to the system. We can use thousands of slip arcs to determine these forces. But it's not the entire story. So Professor Lazinski has used the Bishop's model within the mass for LEM. And again, I want to emphasize, like I did earlier, that it doesn't replace global stability, and it doesn't because of what I mentioned before. All the exit points come out the wall. None of them go under the wall. So global stability has no limitations, and the LEM is limited to the design envelope of the wall structure itself, the infill and the retained soils. Never the foundation soils are below the wall. So really, we're looking at for a complete design, it's a two-step process. So step one, AB walls. AB walls is going to let you do the geometry, the loading, the slopes, the grid lengths, the grid spacing, all of this stuff, and you're going to be able to determine or analyze the internal and the external design requirements within AB walls. But then, in order to make sure the entire slope and wall structure are stable, you're going to need to run a global stability model. And for many years now, AB Walls has had a export feature where you just simply click a button and it exports a file from AB Walls that can be read in RISA. RISA is the global stability modeling program that was developed by Professor Lazinski, and it is extremely easy to use. It's really just exporting the geometry of the wall. So if you're not using RISA, all you have to do is model the geometry of the wall, the lengths of grid, the strengths of grid, the connection, all that stuff. You have to put that in. But what the other programs don't have that RISA does is RISA's been recently released as RISA Plus. So RISA Plus has limit equilibrium built into it, as well as a standard global stability modeling. So I would encourage all of you to take a look at it if that's a program you do not have. So the two-step process is ultimately what ensures the overall stability of the terrace structure from top to bottom. So again, this has been an overview of AB walls plus terraces and an overview of the high points of limit equilibrium. If any of you want a more in-depth conversation on limit equilibrium, please call me. I have no problem talking shop. It's a great new tool in our pockets to do designs. I've been fortunate to be able to work with Dove after he developed it, along with NCMA, to work on how we can bring it into segmental retaining wall design. And AB Walls plus Terraces is really the culmination of that. And I really hope that all of you will schedule your time next month, February 27th, for a full 1-hour advanced tutorial covering the ins and outs of using LEM in the program. And 1 hour of continuing education credit will be available for that session, not for this session because of it being an overview. And I will include a registration link on the follow-up email that I'll send you guys all out tomorrow. And again, feel free to reply back to me as well. If you, just to recap what I said earlier, AB Walls plus Terraces will be out in hopefully next coming days. We are really shooting for the end of January, which is next Friday. We're going to be close, but we do all our programming in-house. So after it's released, we want to make sure that it's as accurate as possible and user friendly without any bugs. That's what we're doing right now, is making sure it's working. And if you ever see anything on the standard side or the Terrace side, please let us know, because again, we do our programming in house and we can fix it as needed. And then if you have a copy of it, it's just going to be a simple update. So um, on February 1st, double click on your icon, and crossing my fingers, it'll be there for you. It'll just be a simple pop up. Say yes to the update, and it'll be that simple. If you do not have a copy of AB Walls, feel free to go to engineering at Allen Block and email a request for that. Reply to the email I'm going to send you tomorrow, or you can find this icon that I've got at the bottom of the screen on the Designer tab of our website. If you go to the home page at allenblock.com, in the upper right corner, click on Designers. Just scroll down a little bit, and you're going to see this icon, and you'll be able to request a copy there as well. So with that, I'm going to wrap it up, and feel free to text me any questions in that question bar, or again, just reply back to that email. You'll get probably sometime tomorrow morning after the other sessions are completed. So I appreciate the time and look forward to working with you all in the future. Okay, well, it looks like I don't have any questions at this time, so I look forward to any that you send me in the email, and I wish you all a great day, and happy designing with the new AB Walls program that'll be out very soon. Thanks a lot, and have a great day.